Good day, I'm Dr. T and welcome to my office. Today I would like to talk about human society and our relationship with various Earth systems. We're on the Earth. It's an island floating in space. Effectively, the farthest humanity has gone is a little bit past the moon. We've sent robots to the edges of our solar system. We're mostly located here on Earth. And things like asteroid mining, etc. are still science fiction, although hopefully not for the too awfully distant future. That said, I'm not getting my hopes up too much. Everything we need for life needs to come from our planet and the various systems on our planet. So I want to look at how our obtaining of stuff, the things we need, and the energy we need to run those things impacts Earth systems and how they relate to those. The first topic I would like to dig into is that of electricity. Of course, electricity is a common way of powering things. Most of our homes run primarily on electricity, although that does vary from location to location, and nowadays even forms of transportation are run by electricity. But electricity is less a source of power than a way of transferring energy from one location to another. Remember, you don't create energy, you simply transform it from one form to another. I want to look at our ability to transform energy from something into electricity so then we can do some work at our home, office, or job site. Now, there are multiple ways of creating electricity. Most of them are going to involve something spinning. So let me talk briefly about a few topics that don't involve something spinning. And by the way, I am not going to be covering all possible ways of converting one form of energy into electricity. There are more ways than what I want to cover. I want to hit kind of the big interesting ones. When it comes to things that generally don't move much, they're not spinning, photovoltaics have got to be on the top of the list. These are growing in popularity as we're getting better at building these guys. Photovoltaics take light from our sun, so the energy is coming from our sun, so fusion taking place in the sun, sending off radiation that's hitting the photovoltaic cell, and at this point causing electrons to split away from their internal atom, migrate to one side. The whole, basically the shuffling of electrons around, goes in the other direction. They complete the circuit. Bada boom, bada bang, you've got some nice DC current going on. Now you've got a couple other options. You can do a thermogenerator. This uses a couple of layers of different metals to have a similar effect. These are, however, used generally on relatively small scales, so I'm not really going to touch much on them. Additionally, we have fuel cells. Now, you are going to get some moving parts in a fuel cell, although not nearly as much as you would think. Fuel cells are basically batteries, except for the reducing agent and oxidizing agent are going to flow in and out of them, thereby allowing you to continuously replenish them. Typically, fuel cells are used heavily with hydrogen, but also methane is popular for fuel cells. This is a growing technology, not one you see a ton of, but becoming more used specifically in more specific applications where they meet the needs of that particular application. I want to jump into areas where we take some form of energy and we make something spin in order to make electricity. What we're going to do is we're going to set up a generator. A generator is, roughly speaking, a big magnet. This is honestly usually an electromagnet, so you take a DC power source to make an electromagnet for the stator, the part that's not moving, although you can do this with a permanent magnet. And then you rotate a rotor. Yeah, we're not too original in naming. The stator stays and the rotor rotates. That rotator is going to have a loop of wire on it. Now, as that wire rotates through the magnetic field, you're going to change the magnetic field around the wire, thus inducing an electric field. And during one part of the rotation, it's going to go one way, and the other part of the rotation is going to go the other way. Therefore, you create some nice alternating current. Now, the reason we like alternating current is that you can plug it into one of these critters. This is a transformer. Basically, you're hybridizing an electric generator with an electric motor, both AC. The fact that the current is alternating means you don't actually have to have any moving parts, and the number of windings on each side is going to dictate what happens to the voltage. This way we can increase or decrease the voltage actually quite a bit with this. The reason we might want to do so is that transmitting electricity over long distances is more efficient if you do so at a high voltage. As such, in general, we use alternating current for most applications. That way we can ship it relatively easily long distances. For those applications using, say, electronics, typically we use DC, and for those applications where we want to send it an incredibly long distance, like multiple states, we actually, oddly enough, switch back to DC. Due to the magnetic fields involved, it's actually even more efficient, but it's an absolute pain to get it up to those high voltages. Now, I showed you the generator earlier. That's a bit of a myth. That is a generator, and that would work, but typically we don't use one that looks like that. Instead, it looks like this. Sorry for the lower quality image. It's what I could find on Wikipedia. You'll notice the difference here is that there's more wires. Instead of having one loop inside the magnet, we have three, and they're off axis. So they're rotated roughly every 60 degrees, so it kind of looks a little bit like an egg beater. The idea here is that we're cramming more wires into the same magnetic area, therefore allowing multiple currents to be flowing a little bit easier. You generally get a little bit of smoother transition because with alternating current you get a burst of power and then it goes down, and you get a burst and goes down and burst, etc. This way you get 3 bursts off sequence, and such you can transmit the power nice and smoothly, less pulse-like. Additionally, each one of these wires are going to create a magnetic field around them, but because they are off sequence with their pulses, that magnetic field is going to be different and their magnetic fields are going to cancel out, allowing for a somewhat more efficient transfer of electricity and less impact on the local area. Although at high current, these will still generate a fairly meaningful magnetic field. So it does not eliminate the magnetic field, but it does increase efficiency by allowing the magnetic fields to somewhat cancel themselves out. Now, once we transfer this over, if we go back to the grid, we're going to have whatever our power plant is, whatever our generator is, we're going to go into a transformer. It's going to step up the voltage for transfer. It's then going to get to wherever it needs to go. We're going to drop the voltage down and then start distributing it out. Now, it's not quite this simple. Generally, there's several steps. Different consumers want different levels of voltage, so you may have some consumers that want a fairly high voltage going in, depending on what they're doing. These are definitely some form of industry of some flavor. Likewise, there may be other consumers that want a lower voltage, but still quite high, and residential voltages drop down quite a bit, partially for safety reasons, but also generally a house doesn't actually use that much energy. Something like a factory is going to use quite a bit more. Generally speaking, when I mentioned how electricity usually comes over in 3 phases, so it kind of gets those pulses a little bit off sync to smooth things out, that's definitely useful for individuals using lots of power. For home use, we typically only get one of those 3 phases, and that's actually split in half to give us our 120 volt. Once you put it together, you get your 240 volt, which is what runs, say, your dryer or your oven. Lower voltage, generally safer, and we don't need 3 phases worth of power for a normal residential application. Once again, homes don't actually use that much electricity here. Okay, so we've got our power grid. Now, we'll actually set up our power as more of a web. The image here shows that it's just kind of a power plant to customers, but what we'll do is we'll interconnect a bunch of customers and a bunch of power plants. That way, if something happens to a power plant, we can shift things over and take wherever we're getting lots of nice power from and make up for the times when the power plant is down for one reason or another. Now, let's talk a little bit about how we are going to spin the shaft, because everything I've described so far, all we got to do is turn that rotor. The question is, how are you going to turn the rotor? Wind is in many respects the most direct way of doing this. So you build a big windmill, you put large aerofoils on a rotating hub, you let the wind blow through, that turns the hub turns a shaft, you go through a gearbox to get the speeds right because you want to spin the rotor at just the right speed, roughly 60 times a second for here in the United States, in order to get your alternating current out. fairly straightforward. Now, of course, the wind does vary in speed, so you do want to vary the blades and the gearbox in order to get the optimum speed out of your rotor and thus going into your power generator. But there are multiple other ways, quite a few of which will involve some form of turbine or a series of blades that you run gas through the blades in order to get them to spin. A classic example is going to be that of a gas turbine. This is basically a jet engine. Now, it's been optimized not for thrust. Thrust in this case would be a bad thing. It would make your power plant run away. But instead, it's optimized for torque. So keep in mind when you get your jet engine, or in this case, gas turbine, you're using combustion to spin the blades. That's going to suck in more air and shove it out the back end. But you can then, instead of shoving it out the back end at high speed, you can use that to spin blades, either the same set or more blades. And now you get, instead of thrust, you get torque and lots of high-speed rotational energy, which is great for powering your generator. Now, gas turbines aren't the most efficient things in the world. They work fairly well. You do get a bit of particulate matter out the back end, so you may need to scrub that up. The reason we're concerned about particulate matter is that it can be somewhat dangerous. You can get particulate matter in lungs. The smaller the particle, the further into the lungs it goes. Remember, your lungs are breathing air, not dust. Very small particles can get deep into your lungs and potentially even get into the bloodstream, where they can cause inflammation and damage. So we want to be careful about particulate pollution, and gas turbines, you do sometimes have to worry about that. Now, you could also, by the way, use an internal combustion engine. Those are typically a bit less efficient, used somewhat on smaller scale. Things like generators run it off of diesel or something. But generally speaking, if we're going to have a gas turbine, we're probably going to pump in a bunch of natural gas. Natural gas is fairly popular because due to modern extraction techniques, at least in North America, it is quite cheap and readily available. Additionally, you can run a gas turbine off of it. But you have a bunch of hot exhaust. Now we can spice that up with a combined cycle power plant. So in this case, we're going to run a gas turbine. You're going to get your electric generation from that, but you are going to get a bunch of hot exhaust. That is waste heat. Now, heat is something rather interesting. If you've got something that's really high temperature, that's still useful heat. If it's like low temperature heat, so we're talking something below the boiling point of water, that's much harder to use in a useful way. It's still doable. You could use it for heating something. So if I needed to heat a greenhouse, or if it's a cold environment and I wanted to ship that off and heat houses, etc., some low temperature heat is usable, but the sweet spot is if you can get noticeably over the boiling point of water. In that case, you can do what this critter does. Use the exhaust heat to boil water. Yeah, most of the next ways I'm going to describe making power involve the phrase boil water. So you boil the water, this generates steam. Steam then goes through a steam turbine where the gas, as it boils, it expands, creating pressure, pushes through the turbine blade, so you get that multi-sets of fans. This creates a spinning rotation and therefore spins your wires on your rotor, creating power with your generator. You then recycle the water. You do want to recycle it, not just flush it out the back end, because this needs to be fairly pure water. Otherwise, any sediments are going to clog up the whole system. So whenever you're doing this, you want to have very, very pure water within your boiler, potentially with protecting agents within there to protect the whole system. Now, let's talk a few other ways to boil water, because that's where I'm going to go with the rest of this. We could use geothermal energy, so we could grab energy from the ground. If I've got volcanic activity relatively close, not too close, you don't want to put this on the volcano, because, volcano. But if you've got a place like, say, Iceland, where volcanic activity is relatively nearby, you can drill a nice big hole, and it's actually a pain to drill a hole. This is one of the major issues. But if you can drill a nice hole, not too horribly deep, where you can get some rocks that are really hot due to volcanic activity, then you can pump water in one hole and then extract steam out the other holes. Turn a turbine, bada boom, bada bang, you've got some electricity. So geothermal works great. It's an absolutely awesome way of doing things. The only major problem is that you're extremely limited on where you can boil the water at because you need volcanic activity relatively close to the surface. Holes are an absolute pain to drill, and so if you've got to go down a really long distance, this is not going to work for you. Now, we could boil water by burning something. Oil, coal. Coal is the traditional here. So I can take coal, I can burn the coal, I can boil the water. I'm going to recycle that water, so I'm going to have something to cool it off. Those large kind of weirdly shaped towers, those are cooling towers. You normally think of those as a nuclear power plant, but coal plants can use them as well. Or you could dump the heat into a river. Now, of course, all that heat going into the river is going to affect the ecosystem of that river, so that can be a bit of a problem. But you boil water, you turn a turbine, you turn a generator. Yay, works well. Now with coal, you got a couple of issues coming off. One, you get what's called coal ash. Not all of the coal is pure carbon. Coal comes in a couple of different classes. You've got lignite, which hopefully is not what you're using, although it is used for power generation. This is poorly processed coal. Basically, it's peat that's been partially squished into sedimentary rock. It's got a lot of random other junk into it. A lot of it is going to be various mineral components, water, etc. So you're not going to get a lot of heat out of it. It's going to create a lot of ash. The most popular is bituminous coal, and I should say there's an in-between sub-bituminous coal, which is kind of between bituminous and lignite, but I'm just going to skip straight to bituminous coal. This one is a sedimentary rock. It's been pressed underground long enough that's kind of squeezed out a lot of the impurities, but by no means all of them. This is generally the preferred because it's relatively available, so the price is reasonably cheap. It's got a lot of small volatile organic molecules in it, so it burns nice and hot, nice and quickly. It leaves a medium amount of ash though, so you've got to deal with that ash. And the ash is actually a fairly serious problem because now you're concentrating all of the other miscellaneous minerals that were in the coal, including lots of heavy metals, things like arsenic and whatnot. As such, the giant piles of ash become a serious hazard. And they are also quite often radioactive because of radioactive isotopes that you've now concentrated. Things like uranium and the like. Not highly radioactive, just well more than a random rock. You're also dealing with a lot of carbon dioxide. The natural gas has the same problem, but generally speaking, gas turbines, especially if you then do the combined cycle, are going to be more efficient, so you generate less carbon dioxide per kilowatt hour of power you generate. So carbon dioxide, let's talk a little bit why this is a bit of a problem. And to do so, I need to talk more about cycles. If you notice, the last several videos talked a lot about cycles. I had the water cycle, the rock cycle, and in this video I'm going to talk about several other cycles. We're on a planet. The matter more or less just stays here, so it kind of cycles through our planet. As such, you've got carbon. Carbon could be in our atmosphere, generally in the form of carbon dioxide, a little bit of carbon monoxide, but mostly carbon dioxide. But it could also be in the biomass, so the biosphere. It could be dissolved in water, typically in the form of carbonates. Or it could be in the lithosphere, so in the geology, potentially in the form of coal or petroleum or carbonate rocks. So you have a bunch of different locations for the carbon, and naturally this cycles through. Some goes into the atmosphere, some gets trapped into water, some gets trapped into the geology, and some of it's bouncing around the biosphere and going between all of these sources. So you get this constant flex. Now, as we burn fossil fuels, coal, petroleum, natural gas, as well as react carbonate-rich minerals, we release carbon dioxide into the atmosphere. We're doing so at a much faster rate than Earth processes are taking it out of the atmosphere, and thus we are increasing the amount of carbon in the atmosphere. This changes our carbon cycle. Now, this is going to have effects. Some positive, mostly negative. The slight positive is it does make life a little bit nicer for the plants, but just a little bit. And the negative ones are generally going to outweigh the positive benefits by a lot. The main issue is that carbon dioxide absorbs quite well in the infrared, and therefore is going to affect infrared light traveling through the atmosphere. Remember this image from that really long atmosphere video? As heat from the sun hits the Earth, it's radiated back off into space, generally in the form of infrared. And the atmosphere is not exactly transparent to infrared. So the infrared goes up into the atmosphere, heats up one layer, is re-emitted, and this process of heating and re-emission takes place until it reaches a nice equilibrium at each layer of the atmosphere. By the way, this image, I just picked a couple of layers. I didn't try and model the entire atmosphere. But as you increase the amount of carbon dioxide in the atmosphere, as well as other greenhouse gases, such as methane or even water, the distance that the infrared light travels before getting reabsorbed goes down, so you're effectively adding more layers to this atmosphere. As such, the equilibrium shifts so that the equilibrium temperature on the surface ends up being higher than it would have been if there were less infrared absorbing molecules within the atmosphere. And of course, a hotter surface is going to affect things like climate and ecosystems, as well as things like the water cycle and whatnot. So this has a lot of impacts. So adding a bunch of greenhouse gases to the atmosphere, maybe not ideal. Once again, though, we do want our electricity, so we get this kind of trade-off, one that maybe we would like to move in a somewhat different direction. In fact, we have been moving in a somewhat different direction. If we look and compare 2000 to 2024, the blend of power sources that we use, and this is we here as the United States, has shifted, and we have shifted to lower and lower carbon options. There's two more power sources I want to bring up before I move on from this point of the video. Let's go nuclear, another way of boiling water, this time with spicy rocks. So we're going to undertake nuclear fission, so we're going to split heavy elements apart, in this case uranium, by bombarding them with neutrons, and that's going to release heat. That heat is then going to be used to boil water. Generally speaking, this is a pressure-based reactor. You're going to heat up, or actually superheat water that's going through the reactor core. Because the water is going through the reactor core, it's becoming contaminated with radioactive nuclei, and thus is radioactive. You don't want that bouncing around too awful much, so you then use a heat exchanger where that water boils water into steam. That turns the turbine. You have another heat exchanger to cool off the water you just boiled, because that needs to be really pure water, and you'd rather not just vent that off to the atmosphere and keep purifying more and more water. That would be way too much of a pain. So you use another set of water that you can then vent off to the atmosphere, or hopefully recycle at least to some degree. That's what those big tower things that we usually think of a nuclear reactor. The nuclear reactor is actually a small thing, usually located inside a rather well-built building, because you don't want that thing breaking. Of course, nuclear power plants do have the problem that that material doesn't just go away. You are left with radioactive waste that thus needs to be stored and disposed of. It will eventually decay and no longer become radioactive, but that is not on human timescales. We are talking tens of thousands of years, which is a real pain. Okay, let's wrap this part up and talk about hydroelectric. So for hydroelectric power, you're going to utilize a dam in order to create a lake. And if you're able to hold the water high on one end, low on the other, you can let the water from the high end down to the bottom end. Good old gravitational potential energy. And in the process, you can make it spin a turbine. Now, a couple caveats on this one. One, we've kind of already installed all the hydroelectric dams we can, because you need a good location for these things. And there's only so many good locations for nice hydroelectric dams. And we really went on a big dam building approach back in the 30s. So we have built a lot of these things. Second, hydroelectric dams do change the local environment. You're taking a stream or a river and turning it into a lake. This is going to dramatically change the ecosystem. Now, hydroelectric dams do have an interesting benefit, though. They can provide grid-level storage. So electricity, so far as I've described it, needs to be created and used almost instantaneously. So if you have a power system that's got any kind of intermittent to it, which of course solar is going to have an intermittent power production because, solar cells don't work at night. Wind also is going to be somewhat intermittent as the wind has to blow, although the particularly large, tall windmills are much more consistent because they're able to tap into higher level stronger and more consistent winds than the smaller ones. This is one of the reasons why windmills have gotten so much larger over the last 30 years or so. The higher the windmill, the more consistent, and just simply the more power you get. Now, if you can take your hydroelectric dam, you can run it in reverse. You can turn your generator into a pump, or you can have a separate set of pumps, to be honest. And you can pump water from the bottom part up to the top. That way, you can start storing energy. You can make it into a gigantic battery. This is helpful because energy does fluctuate as well as the demand. So let's look at this. This guy is a duck diagram. Okay, it's a little hard to see the duck, but what we're looking at, the top blue line is total load. So basically, at what time of day did people want electricity? When you flip on that light switch, the power plant has to give a little bit more energy to power your light bulb. And what we find is that in the wee hours of the morning, load is typically a bit lower. And once everyone's coming home at night, load generally spikes as everyone's coming home, cooking dinner, turning on the TV, cranking down the air conditioner. Air conditioning, by the way, takes a ton of electricity. It's one of the dominant uses. Now, if we look at the amount of power that the solar generates, it gets most of its power when it's sunny. Obviously, it's turning sunlight to electricity. So it basically gives you nothing at night, and it's going to ramp up and then peter off. So it's not lining up with peak demand. As such, you've got to make up that energy from someplace else. Now, let's look at this other graph. And this one is looking at the idea of what if we can add in some storage. Grid level storage, either in the form of hydroelectric or literal batteries. Several years ago, this was more on the lines of sci-fi. Hydroelectric totally worked, but battery technology wasn't there. Nowadays, battery technology is getting there. I wouldn't say we're there, but we're definitely making a dent with our battery technology. So the idea here is that solar generates quite a bit during the day. You've got other sources generating power. And if your demand ever is less than the amount of energy you're generating, you can use that to charge batteries. Then when the amount of energy you're generating drops below demand, you can use your battery stored electricity in order to create power. You can definitely use this with hydroelectric, but nowadays with the use of batteries, or sometimes actually giant flywheels are another area to discuss, doing grid level storage. This can make renewable sources of energy, which are typically much more intermittent, much more viable. Additionally, if you can ship energy for longer distances, that is also going to help mitigate the intermittency, because if the wind's not blowing in one place, it may very well be blowing someplace else, so you can shuffle your electricity around. Now, when it comes to shuffling electricity around, that does come with a price. As electricity is traveling through wires, it's not perfectly efficient. You are losing some energy due to heat production and due to interactions with its magnetic field. The higher the voltage, the more efficient you're going to be, because you have less current, less heat, less magnetic field, but you are still going to lose some electricity due to inefficiencies. This then frames a couple of different ideas for power distribution systems. See, we have a grid of power. We've got multiple power plants interacting with many, many consumers. Here's kind of a global map of power grids. If you look at the United States, we basically have three power grids: East Coast, West Coast, and Texas. The reason you got a grid is that if one power plant goes offline, then you can shuffle around your power and redistribute it so you don't lose power to your consumers. The reason Texas is its own grid is that the other grids have certain standards that they want all power plants to produce, and the Texas-Oklahoma grid did not want to meet said standards. We kind of saw the outcome of that a few years ago when there was a massive ice storm. The natural gas lines froze up because they didn't get the water out of their natural gas lines, and the natural gas power plants went offline, and it was massive blackouts in Texas. Windmills were also affected, but it was really the natural gas plants that were the major problem because there was just so much more of them, and they were very unprepared for freezing weather. I mean, it's Texas, I understand, but they do get snow. I did live there for 2 years. You do get winter in Texas. It's just not very often. Now, you can do a centralized grid, and just generally what we have done so in the past. You've got large power plants. These could be, nuclear reactor and its associated equipment. You could have the combined cycle natural gas plants, large solar fields, large wind fields. And in this case, you're usually banking on economies of scale. Making something twice as big may very well get you more than twice the power or cost you less than twice as much. Wind, this is definitely the case. You generally in the past don't want little nuclear reactors. They're less efficient and more maintenance, although there is approaches to making small modular nuclear reactors, so that could actually be changing. I do not know where the technology is there or the economics. But typically speaking, large nuclear power plant, large coal plant, large power plant was more efficient at generating energy, or at least cheaper to generate the energy, and thus you would ship that energy over a long distance in a grid that was relatively simple. You've got producers, you've got consumers, and then you have a grid that's maintained. And you've got to constantly shuffle around where the power is going because the amount of power produced and the amount of power consumed have to match. If you produce too much, that power is going to go somewhere, and it's probably to breaking the grid. If you don't produce enough, then the grid also breaks. It needs to have a nice match worth of power, which does mean some complexity. Now, an alternative approach is what's known as a distributed grid. Basically, we just take the grid we have now, but we make it way more complicated. In this case, you take things like photovoltaics. The economies of scale doesn't really work that much with photovoltaics. It does, don't get me wrong, but it's not unreasonable to put a bunch on your house, have an inverter to go from DC to AC, and power your house and feed back into the grid. But this whole electricity goes one way or the other, where you're using the grid like a battery, yeah, that adds a lot of complexity. Not to mention you're probably adding solar to this, and solar is very intermittent, so that's a little bit more complexity. You definitely want to get some grid storage going on here if you're going to do this too much. But this is known as a distributed power grid. The distributed power grid does definitely increase complexity. You're definitely going to need computers running this thing, which of course wasn't an option back in the 1950s, but this isn't the 1950s. This also gives you some reliability. We can do like a internet network, and if there's a problem in one spot, we can reroute things very quickly using computer systems, and it becomes a little bit less efficient, a little bit less ideal, but you don't have giant, massive blackouts, hopefully, as we have seen on a few occasions where they take out like most of a grid. I lived through one of those back in the late thousands. Power was off for like a week in Ohio. It was rather inconvenient, to say the least. Now, there are advantages and disadvantages of both systems. The graphic I have here definitely makes you think the distributed power grid is the way to go. They also put the windmills on the distributed power side. They're more on the traditional power side. The economies of scale really do impact windmills. My personal thought is a hybrid system is most likely going to go online, where we become more distributed because, centralized isn't like the power plant and everyone feeding off. It is still a grid, but I could see a much more distributed grid, but not necessarily quite as far as the particular posters may be suggesting. It depends on how you want to interpret said poster. So I'll leave that up to your interpretation. Okay, so I do want us to think a little bit critically about distribution of power, and an interesting application where a distributed power grid kind of makes sense even though we're not usually doing power per se. Let's talk water heaters. You probably want warm water at home. You want to take a nice hot shower, or at least not a cold shower. You may have your preferences. Some of you might. No judgment here. But you probably want a device somewhere in your house so that you can have hot water. You're going to need energy to heat the water. You go to your big box store, traditionally you've had two choices. You can have an electric water heater, or you can have a gas water heater. The gas water heaters are actually surprisingly efficient. You burn the gas, it has fairly high efficiency, and you make a lot of nice hot water. Electric water heaters are, in terms of electricity-wise, completely efficient. All the energy that you're using in that water heater, 100% is going into heating up the water. Resistive heating is actually insanely efficient. There is a catch on efficiencies, though. While the water heater elements are completely efficient, at basically 100%, whereas the gas burner is fairly efficient, but nowhere near 100%, getting the electricity from the power plant to your water heater and manufacturing the electricity is not 100% efficient by a long shot. So the efficiency, the waste energy leaving the system happens in a gas water heater in your house with your chimney, whereas with an electric water heater, it happens at the power plant and with electric transmission lines. As such, depending on the efficiency going in, ends up being which one is more efficient. Generally speaking, the gas water heater is actually going to be slightly more efficient, would be less than the amount of energy lost at the combined cycle gas power plant and the transmission lines combined. Now, there's actually a new breed of water heater on the market that uses a heat pump, basically an inside-out air conditioner to heat water with ambient heat around it. It does take electricity, but it's able to increase the temperature of water more so than the amount of energy it puts in, which is definitely kind of a cool way of running. It's an inverted refrigerator. Okay, this video is getting kind of long. I'm going to split it into 2 videos. So until the next video, have a wonderful day, and I will see you then.